Uh, okay, it seems like I'm live now. So, hey guys, welcome to another live stream by Sham Gupta. And here in this stream, what we are trying to do is we are trying to learn about activation functions in Pytorch. And I hope you like it because if you like it, I'll try to do more of this stuff often. So, what I have planned for you is like we are trying to just learn about activation functions. It's not going to be a much longer stream, it's just like going to be 10 to 15 minutes, and then we will stop streaming. That's it. So okay, cool. So let me just do a quick audio check first and we'll start right away. Okay, seems cool. Okay, cool. Okie dokie, we are live. Okay. So what I have planned is, let's go into Kaggle, make a notebook and use that and publish that notebook so that you guys can refer it later. Okay, so let's create a new notebook. Okay, by the way, the link to this notebook will be down in description after the live stream ends, so hit me up with any doubts if you have anything, right? So let's name it as activation functions with Pytorch. Okay, and delete this cell and I'm gonna start a session. Okay, let's start a session. Cool. If my voice is a bit low, let me increase it a bit, and we'll start with activation functions. Okay, but firstly, why do we need activation functions? In the neural network, you basically require 3 steps, right? So the first one being your x, right? The x being your input vector. Okay, second being your okay, let me just make sure it's marked down. Yes, so the first thing here is your x, the second is your weight, third is your bias, the fourth and the most important one is activation function, because of which you get your scaled outputs, right? Activation function is actually needed because it decides basically whether your neuron will fire or not. That's the very basic definition I can give you right now, but in this notebook we'll try to explore that only, right? So you need 3 things initially, that is 1, weight, input vector, b for bias, BIAS, and the third thing that you require is an activation function. Okay, right? Now how do we package everything together? Let me tell you that. So in a neural network, what happens is you have sort of this equation, this linear equation, right? Now everything which is linear, like if you have to make a linear model, then go for a linear regression model. Then why are we even using neural networks? Because so that we can use it to train for something which is non-linear and generate stuff which is, you know, more fitting to random stuff rather than, like, you know, which is not possible with linear stuff, right? Let's go with the standard equation, which is x when multiplied with w plus a bias is equals to, yeah, like this is the standard linear equation, right? But so your y is equals to, y being your output, so y being your output, it says that you have x dot producted with w plus your bias term. But now how do you apply an activation function over it? This is a linear function, right? So let me write it down here. This is a linear function. Okay, but to make it to make it more fitting to non-linear data, we use specialized activation functions, right? Activation functions, right? Like various activation functions. Okay, so if I say that y is equals to, let's say, function being as f, so you encapsulate everything like this whole term into this stuff, right? Let me just give it that. Okay, so now you have applied an activation function over your whole linear thing, so that now it becomes non-linear. How it becomes non-linear, we are going to just see that right now. Okay, let's get our hands dirty with using Pytorch, right? Let's not waste time and get straight into the video. It's just going to be 15 to 20 minutes of live stream, nothing more than that. Okay, so let's import torch, right? The first activation function we are going to learn is a sigmoid activation function. Now, sigmoid activation function is the most used and standard activation function, which was used like in very old times when no one was there. Sigmoid function was there to help you out for, you know, transitioning from linear to non-linear stuff, if that makes sense. So let's first learn about sigmoid activation function, AF. Okay, anyways, so this is sigmoid activation function. How do you go on to implement that? Let's import torch. Let's import matplotlib dot pyplot as plt, and you're gonna say torch, no, let's say x first. X is equals to torch dot range of -5 to 5, and with a stepping of 0.1, and you say y as equals to torch dot sigmoid. Well, I do have my references, so I'm not going to make errors right now, because if I make error, it's going to be a long video. Okay, and all we have to do is to just say plt dot plot x y, but since this is a tensor, you have to say numpy, right? Because you cannot plot, and with the help of matplotlib you cannot plot a tensor. You have to convert it to a numpy array, right? So you do it numpy, cool, and you just say plt dot show, the standard stuff, and you get a beautiful looking graph. So this is your sigmoid activation function, which basically just transformed this simple linear array of x into a scaled non-linear it just transformed it. You can see that, right? That's it. Okay, cool. So what do we do next? Let me just see, minimize. Okay, so as you can see, this stuff actually saturates when it goes to the top, right? So you cannot have anything like, you know, if anything goes which is maximum, it just saturates it, right? And because of this, you get a problem called as vanishing gradient and exploding gradient, because if something is coming down here, it just touches to 0 and just the gradient gets vanishes, right? And if any value is there which gets scaled to 1, the gradient sort of like just explodes, right? So hence we call this problem as an exploding and vanishing gradient problem. You can research about this a lot on Google, but right now we are just going to cover it like that. So to solve those types of problem, you have different types of more activation functions. The one we are going to see again is tan function, relu, leaky relu, elu, right? So these all types of activation functions actually prevent such kinds of scenarios, right, where you get an exploding gradient problem. And if I have a formula of it, I'm just trying to paste it if I can. I'm not telling you, I'm not promising anything. Okay, let me just take a screenshot of it. If I can, right? So just for your reference, you guys can refer to this image over here. So this is your old school sigmoid activation function. Now let's go to TANH, right? TANH is just another variant of sigmoid. So the same problems which was in sigmoid was also followed in TANH, I guess. Okay, cool. Yeah, so TANH. Okay. So TANH function, it's just another variant of sigmoid. The only difference between sigmoid and TANH is that sigmoid scales any linear function into 0 to 1, whereas TANH scales it from -1 to +1, right? That's the only difference you have, nothing else. Just another way of sigmoid which transforms, which basically squashes, should be the right, squashes, that's correct, right? Data into range of -1 to +1, correct? So that's just TANH for you. Now how do you go on to implement that? That's very easy. Let's copy this example again and paste it down here and just change the TANH, change it to TANH, right? TANH, if I can do that, yeah, it works. So you can see that if you have a value or a data set, you just transform it to -1 to +1. That's it, all you have to do. Okay, the next big thing here is a ReLU activation function. Now ReLU activation function actually stands for rectified linear unit, and it's the most important activation functions in the modern deep learning frameworks, because it works just fine. Now how does it work fine? Let's just get to know that. ReLU, is it correct? ReLU, it is rectified linear unit. Okay, cool. So I have to turn off my camera for a bit, right? Thank you. Anyways, so what do we do here is rectified linear unit actually stands is a ReLU. So this stands for rectified linear unit. So this is the most important functions in modern, you say, in space, neural network space, right? If that makes sense. But so like, because it's really simple, it doesn't have anything, you know, superficial. Now what do I mean by superficial? I'll just tell you in a bit. Just hang on for a minute. Okay, now if I just copy this again and I paste it again, I do not have to import something very fancy. I just have to say, I guess it stands like ReLU. So you make a ReLU activation function, you will go like torch.nn.ReLU, ReLU, if that's correct, right? Okay, ReLU. And what you have next is simply not such stuff. You just say ReLU and boom. So what ReLU is, it squashes everything to 0, right? So if you have anything, right, if you have certain value which is in negative, right, so all the negative values is squashed down to 0, right? But if anything is positive, it scales it linearly. So if for 1 you get 1, for 2 you get 2, right? So this is called as rectified linear unit. And okay, now this Tanich, ReLU were significant improvements in the history of activation functions. But the reason, if you ask that why we still do not use activation functions like ReLU, or like this ReLU was like a groundbreaking activation function which was introduced in 90s, but why is it not used, and why the versions of it like Prelude or Prelude and another name was Leaky ReLU, right? Why were this used? So these were used to actually counter the problem of dying gradients, right? So the vanishing gradient problem becomes a permanent issue over here, because the gradients, if anything is in negative, it becomes directly to 0, and you do not even get a chance to somehow just scale them to a positive side, nothing like that. So this activation function stuff actually these variants of this activation function helped you to there was this choice of these activation functions which made which countered this vanishing gradient problem. So how do you do that? So these versions of ReLU countered the problem of vanishing gradients, right? That's it. And why and how was it able to do that? Let's just check on it in a minute. So I'll just copy this code again, I'll paste it down here, and I'll say not ReLU, but let's say PR ReLU. It's PR ReLU stands for parametric ReLU, and Leaky ReLU is also the same, but yeah, almost the same. So we are going to learn about PR ReLU, that is PRELU, if that's correct, right? And you say something, if I can have this, right? So you have number of parameters as 1, okay? So that's it. Okay. So we make it PR ReLU, we are making it PR ReLU. Now when I run this cell, you get to see the contribution it made to the community and to the deep learning space, because now you do not have to use like the earlier one. We had everything squashed down which was negative to zeros, right? So if anything, if your value in your data set is -1, or if you are getting an output from here, your wx plus b is becoming a minus entity, you get squashed down, that value gets squashed down to zeros. But now if I run it, I get everything squashed down. Okay, that requires detached or tensor. Okay, I can do that too. I guess this was PR ReLU, right? This was a range. Why is it not working? Did I do something wrong? Okay, let's try doing detach dot numpy if it works. Yes, cool. Okay, so if anything is in negatives here also, it won't get squashed down to zeros, and zero means nothing, right? But it will still have some impact of it, right? Because of which you do not have a vanishing gradient problem, right? Okay, so I guess that's clear for now. Okay, so the next activation function we're gonna talk about, let me just check how many minutes are we in the live stream. It's already 20 minutes, But yeah, I'm not gonna take a long time here, so let's move on to okay, this stuff again. So the last activation function we're going to study here is called as softmax, which is very important, but not many people have. Which is very important because it sort of just outputs probabilities instead of just values, right? Okay, so let me give you an example over here. Softmax. Now, where softmax is used, right? Let's just say, okay, say you have your final layer. So all of you are familiar with a neural network, right? Let me just show you a neural network first. Okay, so this is a neural network. Now, say if I have all these values in this layer and we have to predict whether the image we had was of a dog, a cat, or a bird. Now you have 3 classes to classify over here, but what I want to say is I don't want an exact output as to what's just correct. I don't want this to be 1, this to be both zeros. I want a probability of, okay, how much is the probability of this being a dog, this being a cat, this being a bird, right? So if you have an image and the probability of bird comes up as 70%, this comes at 20%, and this comes as 10%, you can probably identify, okay, this is a bird, right? So the probability of getting your outcome in terms of nothing like very specific, like 1, 0, 0. Instead, you get your outputs as in a range of 0 to 1, and which all sums up to 1. Okay, so when you add all these 3 probabilities, you get a sum of 1, right? So you have a very fair chance of getting to know that what your classes were. So that's a very simple example of softmax. So how do we use softmax and what's the formula for it? So this formula for softmax just being very simple and very honestly, this is just the probability formula you will all know from your 12th class formulas. So you know that it's just the probability, your data divided by the sum of everything, right? So you have a fair chance of getting to know whether this is a dog, cat, or bird. Okay, anyways, let's go to the softmax function squashes the output into 0 and 1. However, the softmax operation also divides, right? So the formula which I showed you right now divides each output by the sum of all the output, divides each output by the sum of all outputs, right? Which creates a discrete probability distribution over k possible classes. So if I say k possible classes, that means k here is 3, like in the example which we saw right now. Here the k is, or the classes are 3, right? So basically you use softmax in your penultimate neural network layer. This is this layer, because of which you get so you do not have to get exact values, you just get something between 0 to 1, and then you can probably identify, okay, what should be changed more, right? Instead of 1 0 zeros or ones and zeros, you are getting us something more describable, because if you have if you have outputs like this is 50% bird and 50% cat, so there's a problem that your neural network is not learning better, and it can be improved in the future, right? And you do not have to, instead when you have ones and zeros, it becomes very difficult, and sometimes it over classifies or misclassifies some classes, and hence we use softmax in the penultimate sort of layer, right? Okay, so I hope I am clear till now. Okay, so how do we go on to implement that? It's implemented using okay, I'm back. Okay, anyways, so how do we go on to do that? We just say import torch, the same stuff which we did right now. It's import torch and import torch dot nn as nn, and you just say want some more cells down here so that I can have it improve. Okay, okay, and then you say softmax is equals to nn dot softmax. If I can do this, tab softmax, yes, nn dot softmax. Then what's your input? Your input will be changed here. That would be touch dot random. If I can have random, I don't want I want random numbers, so I'll just say from 1 to 3 I want some random numbers, and my output should be softmax may x, softmax x, and we just say you just say okay, you just say print y and print x. Now why I'm doing this? To let you know the probability. So now if you are adding this plus this plus this, you get you get a sum of 1. So if I try doing a sum over this, I don't know if it will be possible or not, but if I try doing it, it's not gonna happen. But if I say numpy, will it be happening? Nope. How do I? But this is a tensor, right? So I don't think so it's happening. Anyways, so this is what I want to tell you, that if you have something in the penultimate layer of your neural network, what you just try to do is sort of have this softmax layer, so that if you have 3 classes, you do not have to specifically predict ones and zeros and ones. You just have to say softmax, so that you know that how your model is performing. And I think by that your class for today of on activation functions should be stopped. Thank you for joining in, and I hope you had a great time learning about activation functions, and I hope you got a little bit of understanding as to how activation functions work. And so that's it for today. Thank you for joining. Bye bye.